In this video, we want to take a look at a notion called dimension. We kind of use the phrase already. You think about, R2 as being a two-dimensional space and R3 as being a three-dimensional space, but we have a very strict meaning now of what we mean, what that word dimension means. Okay, and here it is. The dimension of a finite dimensional vector space is the number of elements in a basis. And I throw in as a caveat here that the dimension of the zero vector space is zero. That vector space is kind of an oddity in that it doesn't have a basis, right? Because the only element in it is the zero vector, and the zero vector by itself certainly is not linearly independent, so it can't have a basis. So we just say that the dimension is zero. I think of it as it doesn't have a basis, so the number of elements in the basis is zero because there aren't any whatever. That's zero. And the other ones have however many elements are in a basis. So for instance, in R2, you think of the basis ij, right? 1, 0, and 0, 1. It's got two things in it, dimension 2. R3, ijk, must be dimension 3. And Rn, it turns out, is dimension n. Pn, polynomials of degree n or less, is dimension n plus 1. Think of it for a small one, like P2. Right? P2 is all the quadratic or linear, degree 2 or less. So the basis was 1x and x squared. That's got three things in it. So that would be one more than 2. So 3. So P2 is dimension 3. P5 is dimension 6. Matrices, m by n matrices, is dimension m times n, right? And the standard basis is a bunch of matrices with mostly zeros, but 1, 1 in each of the possible places in that matrix. And there are m times n entries in one of those matrices, and so that's how many things you have in your basis. Now, the problem with all of this is that nowhere have we ever decided that, a vector space can have lots of different bases, but it's never been stated that they have the same number of things in them. You might have one basis with 5 elements and one basis with 17 elements. Which one do you pick for your dimension? Well, the whole rest of this video is trying to essentially say that this definition is a good definition. We're going to prove the theorem here that all bases of a finite dimensional vector space have the same number of elements. So you aren't going to have a situation where you have to choose how many. It'll be the same. Okay. So the definition is pretty straightforward. The counting of how many things in a basis is pretty straightforward. That's easy to do. But the fact that we don't know whether all bases have the same number or not takes a little bit of proof. And I'm going to spend some time on this proof for a couple of reasons. One is to show that the definition is well defined, but others, there's some tools in here that we can use for other things. Okay, so here we go. I'm going to be able to show that all bases have the same number of elements if I can show the following theorem. Right? Let V be a finite dimensional vector space, and let this be any basis. So I want to show now, this has n things in it, I want to show that any set in V that has more than n elements is linearly dependent, and any set in V that has fewer than n things does not span, right? And remember, a basis has to do both. It has to be independent, and it has to span the whole space. So to be a basis, you can't have more than n elements because you wouldn't be linearly independent. And you can't have fewer than n elements because you can't span. So if I can prove this theorem is true, then all bases must have the same number, right? Whatever this n is. So if you got one basis, all other bases have the same number of things in it. Now, in order to prove that theorem, I'll come back to the actual proof of this at the end. I need the plus minus theorem first. And here's the plus minus theorem. Let S be any non-empty set of vectors in a vector space V. if S is linearly independent, and if V is a vector in V that is not in the span of S, then we can create a new set, S union V, and that will still be independent. Right? It's like if you've got, let's say I've got two vectors here, S is these two vectors, right? They're linearly independent. They're not in the same, they're going this way. Now, if I am in, let's say, R3, and I've got another vector here that's sticking off in some other direction, right? Not in the plane of those other two, then the three of these together will still be independent. If, however, I pick a vector that is a linear combination of U and V, it is in the span, then I don't have independence anymore. But if I take something outside of the span, I will have independence. And so that's one statement. And two, so of the plus minus theorem, this is the part one here is the plus part. That if you have an independent set and you add another vector to the set that's not in the span of what you already have, then you still have an independent set. So you can increase independent sets to be bigger sets that are still independent, right? As long as you're picking something that's not in the span of what you already have. Part two is the minus part of it. And it says if the vector V is a vector in S, that is a linear combination of other things in S, then the span of S is equal to the span of S minus that thing. So if I've got three vectors here, and I can see that this black one is a linear combination of these two, then I can throw the black one away here, and the span of these two would be the same as the span of the three that I had to start with. Okay. So that's throwing things away. So the first one is adding and keeping independence. The second part is subtracting and creating and keeping the span the same. Okay. So here's the proof of the plus minus theorem. All right. For part one here, so let's say that V1 up to Vn are the things that are in S. Okay. And the vector V, right, this vector V, is the thing that's not in the span of S. And what I want to do is I want to show that V1, V2 up to Vn together with V is still independent. So I'm going to look at a linear combination of them that adds up to 0. And I need to show that all of the k's are equal to 0. Right? So k1 v1 plus k2 v2 up to kn vn plus this extra kv. Now, if that k here is not equal to 0, then what I can do is I can solve for v. So move everything over to the other side and divide by k. If k is not 0, I can divide by k. And I get that v is a linear combination of v1 to vn. But we said it wasn't, right? V is supposed to be chosen to be not in the span of S. So k has to be 0. Because if it wasn't, I'd have a contradiction. Well, if k is equal to 0, then this equation right here just turns into this equation because this part goes away. And this, I know, has to have all the k's equal to 0 because v1 up to vn is given to be linearly independent, right? If S is a linearly independent set. So this forces all of those k's to be 0. This k was already 0, and so that we have only the trivial solution, which means this set, S union with V, is linearly independent still. So I added something in, and it's still linearly independent. Now, part two. Part two is saying, suppose there's a V in S that's a linear combination of the other ones. So I'm just choosing one of the, S is V1, V2, V3 up to Vn, and one of those, I'm going to call it Vi, is the vector that's a linear combination of the others, right? So Vi is a linear combination of the others. Now, what I want to do is I want to show, what does the statement say? I want to show that the span of S is the span of S minus V. So this set is equal to that set. To show that two sets are equal, I need to show inclusion both ways. I need to show that this one is a subset of that one, and that one is a subset of this one. Well, one of the directions I think is clear. The span of S minus V is a subset of the span of S, right? The span of S includes all the linear combinations of V1 up to Vn, including the linear combinations where there's a 0 in front of this Vi, right? Or what I'm calling the V, which is Vi. So when I look at the span of everything in S except the Vi, that one particular one, that's the same as all the combinations over here that have a 0 in front of the Vi. So all of these are certainly some of those. Everything in here is in there. The trick now is to go the other way. Take something from the span of S and show that it can be the span of S minus that V. Well, if you take something from, let V, oh, okay, this V is a different V. Take a vector that's in the span of S, looks like this. It includes this Vi, but that Vi is a linear combination of the other things in S. So what I end up with is a bunch of stuff. So this V is a linear combination of stuff with the Vi in there, but that Vi is a linear combination of other stuff in S. So you end up with just a big linear combination of the other stuff in S. There's no more VIs in here because these are all V1, V2 up to Vn, but not Vi. Okay? So that means that this is a linear combination of stuff in S minus Vi. So stuff in here is also in there. And let's go big again. So that's the proof of part 2 of the plus minus theorem. If I've got something that's a linear combination of the other stuff in S, throw it out. You haven't changed the span. Okay. So now, back to the theorem that this is the same theorem we had above. If you are in a finite dimensional vector space and B is a basis, then I want to show that any set that has more than n elements has to be linearly dependent, and any set that has fewer than n elements does not span. Now, the textbook that we're using proves part 1 and omits part 2. So what I'm going to do is I'm going to omit part 1 and prove part 2. Although I will mention that what the book does for part 1 is they end up, well, they're trying to show that something is linearly dependent. And they end up with a system of equations that has more variables than equations. And it's a homogeneous system, which means that there has to be infinitely many solutions. So certainly there's not just the trivial solution. Right? So that's how they end up proving part 1. And you can read that in the book. For part 2 here, what I'm going to do is I'm going to assume that we've already proven part 1 and use that to help me prove part 2. So here we go. Let S be any subset of the vector space with fewer elements than this basis. Okay. I should have an if here. If S is not linearly independent, then use the plus minus theorem to keep removing vectors from S, keeping the span the same. And I claim that at some point I'll get to a set that is linearly independent. Because S having fewer elements than B has finitely many. And if I keep taking vectors out of there, eventually I'm going to get down to 1. And one vector by itself, well, one vector by itself I want to say is independent, unless it's the 0 vector. But if I had the 0 vector, I'd throw that away the first time, because that certainly is not going to let anything be independent. So if the 0 vector is in S, throw it away. That doesn't change anything. The point is, I can get down to this other set, which I'm calling S prime. It has nothing to do with derivatives, just a way of saying altered S, right? It's still got stuff in it. Well, all the stuff in it was in S, but we've thrown things away until we got down to a linearly independent set. The thing is, the span of S prime will be the same as the span of S, because I kept throwing away things that were linear combinations of stuff in there. Right? Now, If the span of S is all of V, then so is the span of S prime, because they're the same. But that would make S prime a basis for V. That would make S prime a basis for V. And now I can use part 1 to say that there's a problem here, because S prime has fewer elements than B does, which means that B has more elements than a basis. And if it has more elements than a basis, by part 1, it must be linearly dependent. But it can't be linearly dependent because it's a basis itself. So the span of S cannot be V, right? This is where if you make the assumption the span of S is V, you run into this contradiction that B can't be a basis, but we said it is a basis. So the span of S is not V, which means there must be something in V that's not a linear combination of S. So it doesn't span all of V. That's exactly what we were trying to prove. All right, so that brings us back to the fact that every basis must have the same number of elements, because if it's got fewer elements, it's not a basis because it doesn't span. If it has more elements, it's not a basis because it's not linearly independent. So every basis has the same number of elements, and we can with confidence say that the dimension of a vector space is the number of elements in a basis, and it will not be ambiguous.